In this session, let's focus on a couple of problems that were asked in the year 2024 from the topic central force motion. So in this question, we have a satellite which is revolving around Earth in an elliptical orbit, and the semi-major axis of the ellipse is capital A. Its angular momentum is L and its total energy is E. The orbiting satellite's total energy is E and its angular momentum is L. After some time, the elliptical orbit is changed to circular orbit and the radius of the circular orbit is A. And we need to find if the energy changes or not, if the angular momentum changes or not. So that is the question. Before solving this question, let's build up some concepts. So here we have a satellite and this is our planet. The satellite is revolving around the planet in an elliptical orbit. For any central force motion, we have L angular momentum about center of force, angular momentum about center of force is conserved. This is one property. Another property which is applicable to all central force motion is that the total energy, the mechanical energy, which is the sum of kinetic energy and potential energy, is also conserved. That means if we consider any 2 points, let's say this is point 1 and this is point 2, then the angular momentum of the satellite at point 1, let's say it is L1, and angular momentum at point 2 of the satellite is L2, then L1 is equal to L2. Same is the case for energy. If at point 1 the energy of satellite is E1 and at 2 it is E2, then E1 is equal to E2, because these two quantities, angular momentum and energy means mechanical energy, are conserved in the case of a central force motion in any orbit, whether it be elliptical, circular or any other orbit. By central force motion, I mean force can be written as F is equal to some function of R plus or minus R cap. So instead of considering any 2 points, we consider the farthest point, this point, which is also called aphelion, and the nearest point to the planet, which is called perihelion. So this is our point 1, this is our point 1, and this is our point 2. I am erasing this. Then L1 is equal to L2. We say that the mass of satellite is small m and mass of the planet is capital M. Then L1 is equal to L2 implies M V1 R1 is equal to M V2 R2. Here this is V2, this is V1, and we know that when the satellite is nearest to the planet, then the influence the planet has on the satellite is maximum, and therefore V1 will be maximum. and the force experienced by satellite will be least when it is farthest from the planet, and therefore V2 will be V min. Now use energy conservation. Kinetic energy for point 1 is half m v1 square plus potential energy. Potential energy is minus gm small m by r1 is equal to half m v2 square minus gm small m by r2. So this is v1 square minus v2 square is equal to 2gm into 1 by r1 minus 1 by r2. This is equation number 1, and this is equation number 2. So from 1 and 2 you can solve it. You will get v1 is equal to v max is equal to root of 2gm r2 divided by r1 into r1 plus r2. This is a very important equation. Similarly, you can find v2 is equal to v minimum is equal to root of 2g m r1 by r2 into r1 plus r2. These two equations are important. Now if we use L is equal to mv1 r1, or you can use mv2 r2 as well, because L is equal to L1 is equal to L2. You can use any one of them. So if we put v1 is equal to v1 is root of 2g m r2 divided by r1 into r1 plus r2 multiplied by r1. This is equal to m into root of 2gm r2 r1 by r1 plus r2. So this is the equation for angular momentum of an orbiting satellite in an elliptical orbit. For energy, E is equal to E1 is equal to E2, because energy is also conserved. So E1 is equal to half m V1 square minus g m by R1. If you put the value of V1 in this equation and solve it, you will get E is equal to minus gmm divided by R1 plus R2. This is energy of an orbiting satellite in an elliptical orbit. So these four formulas, one formula is for angular momentum, the second formula is for energy, and the third formula is for V minimum and for V maximum. These four formulas are important. Now you need to be able to write these formulas in terms of ellipse parameters as well. So we know that for an ellipse semi-major axis, there is a semi-major axis which is the distance from the center to this point. This is semi-major axis. It is denoted by A, and this distance, this is from center to this point, this is called semi-minor axis, which is denoted by B. And the distance from the center to the foci, center to one of the focus, this is denoted by C. And there is some quantity which is represented by letter E called eccentricity. This is equal to C divided by A. Another property of the ellipse is that the distance from any point, in the ellipse to the two foci, this is one foci and let's say the another foci is here, then the distance from this point, let's say this point is D, from the point D to the foci, to two foci, from here to here, let's say this is S1, and from here to here this is S2, then S1 plus S2 is equal to constant and it is equal to 2A. This is true for any point in the ellipse. So from this point, if we consider from this point to this point, it is equal to the distance from one of the foci to the point at the minor axis, it is equal to A. Therefore we can write C is equal to root of A square minus B square from Pythagoras theorem. Therefore we can write eccentricity E is equal to root of A square minus B square divided by A. Or we can write E is equal to root of 1 minus B square by A square. Now coming back to our figure, this distance is R1, R2, and this distance is R1. You can see that R2 is equal to semi-major axis A plus the distance from the foci to the center, which is C. This is equal to A plus E into A, because E is equal to C by A. I think we will erase all things and then we can do this. So R2 is equal to, R2 is this distance, this is 0.2, this is 0.1, and this distance, this is R1. So R2 is equal to C plus A is equal to C by A into A plus A. So this is equal to EA plus A is equal to A into 1 plus E. Similarly, you can write R1 is equal to A minus C is equal to A minus C by A into A. So this implies R1 is equal to A minus EA. So R1 is equal to A into 1 minus E. Now let's calculate R1 into R2. R1 into R2 is equal to A into 1 minus E into A into 1 plus E. So this is equal to A square into 1 minus e square is equal to a square into 1 minus e square is 1 minus b square by a square. So this is equal to a square minus a square into plus 1 minus 1 plus b square by a square. So this is equal to b square. So r1 into r2 is equal to b square. r1 plus r2 is equal to a into 1 minus e plus a into 1 plus e. So this is equal to 2a. So r1 plus r2 is equal to 2a, and r1 into r2 is equal to b square, or r1 into r2 is equal to a square into r1 into r2 is equal to a square into 1 minus e square. Now if you put these results, r1 into r2 is equal to b square, r1 plus r2 is equal to 2a, these results in the earlier derived results, then you will get the expression for angular momentum, energy, v1, v2 in terms of ellipse parameters. So that's what we are going to do now. So these were the earlier results. L is equal to m into root of 2 gm r1 divided by r1 plus r2. E is equal to minus gmm divided by r1 plus r2. So in the expression for E, if you put E is equal to r1 plus r2 is equal to 2a, E will be equal to minus gmm divided by 2a. Similarly, in this expression for angular momentum, if you put r1 plus r2 is equal to 2a and r1 into r2 is equal to b square, then you will get L is equal to m into root of gm b square by a. Or if you use the result r1 into r2 is equal to a square into 1 minus e square, you get L is equal to m into root of two gm a square into 1 minus e square divided by 2a. 2 cancels and 1a cancel. So this is equal to m into root of g m a into 1 minus e square. Now let's come back to our question. So first, the orbit was elliptical. In that case, L is equal to m into root of gm. The semi-major axis is given, it is capital A, into 1 minus e square. So this is the angular momentum for the ellipse, and energy for the ellipse, E is equal to minus gm small m divided by 2 into semi-major axis, it is capital A. Now when it is changed to circular orbit, what happens is, we know that circle is a special case of ellipse. So for circle, semi-major axis is equal to semi-minor axis is equal to radius, and it is given in this problem to be capital A for circle. This is the first things we wrote. This was for ellipse. So for circle, E is equal to minus GMM divided by 2A. So energy is same because semi-major axis is equal to radius for circle, and it is given to be capital A. So energy does not change. And L, angular momentum, L is equal to m into root of GM A into 1 minus E square. But we know that eccentricity E is equal to 0 for circle. So L will become equal to m into root of G M A, and A is equal to capital A because semi-major axis is equal to radius for circle. So this is equal to m into root of GM A. You can use the second relation also, that L is equal to m into root of GM B square by A. You can use this relation also. B is equal to A for circle, so this implies L is equal to m into root of GM A square by A. So this is equal to m into root of GM A. Clearly you can see L changes. L is equal to m into root of GM A into 1 minus E square for elliptical, and for circle it is only for elliptical. This is the angular momentum. For circle, L is equal to m into root of GMA. So L changes, E does not change. So there is a particle of mass m. There is a particle of mass m, and it has a non-zero angular momentum L, and it is subjected to a central force potential V of r is equal to k ln r. K is a positive constant. We are asked the radius at which the orbit is circular. So the condition for circular orbit is dV effective upon dr at r equal to capital R is equal to 0. Now V effective is equal to given potential plus L square divided by 2mr square. So this is equal to, the given potential is k ln r plus L square upon 2mr square. Now if you take the derivative, dV effective upon dr, this is equal to k into 1 by r plus L square upon 2m minus 2 by r cube. For circular orbit, we set this equal to 0. So k by r minus 2 cancel, L square upon mr cube is equal to 0 at r equal to r for circular orbit. K by r minus L square by mr cube is equal to 0. This implies K by r is equal to L square upon mr cube. This implies 1 r cancel, this will become r square. This implies r square is equal to L square by mk, or r is equal to L divided by root of mk. So radius is equal to L divided by root of mk. Now there is a second question, if the circular orbit is stable or unstable. To check stability, we compute the second derivative. So we take d square v effective upon dr square at r equal to r, and if it is positive, if it is greater than 0, then this implies stable. If this quantity is less than 0, then that means the circular orbit is unstable. So let's see if it is stable or unstable. So d by dr, the first derivative was equal to k by r minus L square divided by mr cube. So when you take the derivative, this will become minus k by r square plus 3L square divided by mr raised to 4. Now you put r equal to L divided by root of mk, then d square v effective upon dr square will become minus k by r square plus 3L square upon mr raised to 4. When you substitute the value of r is equal to r square is equal to L square by mk, so minus k divided by L square by mk plus 3L square divided by m, r raised to 4 is L raised to 4 divided by m square k square. So this is equal to minus m k square divided by L square plus 3 k square m divided by L square. So this is equal to 2m k square by L square. So this is positive, this quantity is positive, which implies the circular orbit is stable. So the correct option here is A. R is equal to L divided by root km and the circular orbit is stable.